Hey, Become students. First lesson for this one is just going to be a short one on gas mixtures and partial pressures. So you also might recall Dalton's law of partial pressures from 400. Dalton's law of partial pressures. Partial pressures. So basically, all that's saying is that the sum total of the pressures within a mixture is just the partial pressure of each individual gas that they contribute. Okay, so the partial pressure of each gas in the mixture depends on the number of moles of that gas. That's a key component. So if we know the moles of each gas, we can find out the partial pressure of each gas, and then ultimately add them together to get the total pressure, okay, of what's going on there. So one thing that we have to bring back in here, though, is mole fraction, because the mole fraction is going to be important when it comes to the number of, in order for us to figure out the moles of an individual gas. All right, so the mole fraction is just the moles of an individual gas divided by the total moles of gas that are in the container. So you can already start to see, if we're starting to deal with moles of gases and stuff, that PV equals nRT, right, our ideal gas law, which deals with moles of gas, is going to be probably fairly important when we're trying to do this stuff potentially. Okay, so let's take a quick look at the first example here. So we have some helium and oxygen, and and we're loading up the tanks so we can go scuba diving here. So for a particular dive, 46 liters of helium at 25 degrees Celsius in one atmosphere, and 12 liters of oxygen at 25 degrees Celsius in one atmosphere were pumped into the tank with a volume of 5 liters. So we want us to calculate the partial pressure of each gas and the total pressure in the tank. So the first thing we need to do is we have to figure out, we need the moles of each gas before we can figure out what the total pressure is and all that stuff. So in order to do that, notice all the information they give us. They give us a volume, they give us a temperature, and they give us a pressure. And the only thing that we don't know is the moles. Well, PV equals nRT. We have all the pieces to plug in here in order to solve for moles. We know if we look at helium, so we're going to run two problems here, one for helium and one for oxygen. So the helium gas, we know, is one atmosphere. The volume is 46 liters. We don't know the moles. Remember, the R value for our moles of gas here, when we're looking at atmospheres, is 0.08206. That's on the back of our periodic table. And the temperature, we always deal in degrees Kelvin, so we have to add 273.25, so that's 298. And ultimately, when we work that out, we have N is equal to 1.88 moles. And that's for helium, okay? And we also have to do that for our oxygen gas. So we're going to run another ideal gas law problem, nRT. So we have one atmosphere again. The volume is 12 liters. And R is the same. Temperature is the same as well, 298. So for oxygen gas, we get total moles of 0.490 moles. Okay, so now the moles total, we'll just add those guys together to get a total of 2.37 moles of gas. Right? All right. So now we can use the mole fraction to solve for the partial pressure of each individual gas, right? But we still need to know the pressure total in our tank that we filled with the helium and the oxygen. So for our tank, we got to do another ideal gas law problem, right? Because we got to solve for pressure total. And we can use the moles total, R times T. So we solve for P, our volume is 5 liters. The total number of moles is 2.37. We can still use our R value of 8.206. And then our temperature is 298. All right, so we solve for our pressure total. That is equal to, if we work out the math there, it's 11.6 atmospheres, what I came up with. Now you can solve for each individual pressure, because we can use the mole fraction for each, times it by the pressure total to get each. So our pressure of helium is going to be equal to 1.88 divided by 2.37 times our total pressure of 11.6. And that actually gives us our pressure there. And our pressure for oxygen is equal to 0.490 divided by 2.37 times 11.6. And that's going to give us our pressure for oxygen. So that's how we would do that problem. So it's a lot of ideal gas law to find each individual pressure. Okay, so that's the first problem. Now remember, if things are going a little fast or whatever, try and slow the video down. Pause it, go back and see what we're doing here, and work through it with me together. Okay. So on the next problem here, okay, they have the partial pressure of oxygen was observed to be 156 torr. So torr is the same thing as millimeters of mercury. You can treat that in the same fashion. Okay. But you can also notice that on the back of your yellow sheet, they operate in torrs as well for the gas law constant. Okay, so we got 156 torr in air with a total atmospheric pressure of 743. Calculate the mole fraction of O2 present. Okay, so the pressure of O2 would be equal to the mole fraction of O2 times the pressure total. Right?
That video one down.
So, all right. So ultimately, all we need to do is plug this in and figure out exactly what's going on here. So all we need to do here is plug in what we know. So we have 156 torr is equal to the mole fraction of O2 times our pressure total, 743 torr. Right? And we work that out, and our mole fraction of O2 is equal to 0.2099, which is equal to 0.210. Okay, that's the first video for gas laws review number 2. No problem.